Welcome to Walkabout the Galaxy, the self-deprecating astronomy podcast.
We suck.
Well, I didn't say self-annihilating.
We're stupid. We're ugly. What are you going to do?
Oh, boy, I'm sorry I chose that.
Wow, bad week here.
Yes.
Okay.
Yeah. Sorry you came back.
Yeah. What happened last week?
Welcome to Walkabout the Galaxy, the gently self-deprecating astronomy podcast where the science is universal, the opinions are personal, and the trivia is historical. We are Strange, Up, and Top, the Astroquarks, also known as Josh Caldwell.
Hannah Sargent.
And Jim Cooney.
Coming to you from the Walkabout studio at the University of Central Florida. Charm is on assignment at the American Physical Society meeting.
Mm-hmm.
Yeah.
Hanging out with the physicists. Remember to subscribe to us on all platforms, including YouTube, Facebook, Twitter, and Instagram. Our YouTube videos feature chapter breaks so you can cheat and go straight to the trivia answers. So maybe the two of you should wait until the episode is posted to try to answer.
That makes sense.
Follow the Astroquarks on TikTok, where we published a 30-second video once.
Oh, I thought it was like you did another one? No. Okay, just the one.
Nope. Our website at walkaboutthegalaxy.com is being updated with sponsors, trivia, and more. Our first music video, which is on YouTube, is about to be joined by our second hit number. So look for that soon.
I mean, we say soon, but we always make promises.
I was going to say soon on astronomical timescales.
Okay, there we go. Sorry for interrupting.
Yes, perfect. You can contact us anytime at wtg@ucf.edu. Our stumper today is related to some space news, or was triggered by some space news, a fun event that we saw just taking place in the last 24 hours, which is...
SLS or James Webb?
SLS.
Okay.
Yeah, we had two exciting events this week, but with SLS, it's in our backyard here, being rolled out to the launch pad, and it triggered this question for me, because on the side of SLS is the NASA worm logo.
Yes.
Right? Which is this 1970s version of what futuristic looked like, which is a stylized NASA that's called the worm logo because there's no crossbars on these. You could do it as a continuous sort of thing. Mm-hmm. It's not continuous, but each one is a worm. So what's your preference? The NASA worm logo or the original and then resurrected NASA Meatball, quote unquote?
What's that one look like?
What does it look like? Dude, the NASA Meatball, it's a circle, it's a blue circle with stars. It says NASA, and it has a sort of a chevron shape that's sort of meant to represent aeronautics, and then it has a sort of orbity thing going around it. It protrudes a little bit beyond that blue ball. I don't know. It's not meatball colored. It's called the Meatball.
It is called the
And the worm, and we'll be coming back. That'll be part of our trivia, actually, coming back to these
worms.
logos.
Oh, no.
Worm-related trivia again?
Our trivia
Awesome.
is NASA historical. It's not worm related.
Bummer.
It's NASA historical. So what do you think? Worm or meatball?
I really like both of them. Like, whoever came up with each of these designs, like...
Hats off.
Yeah. I really enjoy both of them, and I don't want to have to pick.
Okay. I don't know if that... I'm not sure if you're allowed. Let me send that off to the rules committee and turn to Top Quark, see what he thinks.
Meatball!
Classic Meatball.
Classic Meatball.
Yeah. Okay.
Yeah. I'm not that big a fan of that kind of 70s futuristic look thing. That it's fine, but just as a general aesthetic,
Yeah. The judges have come back and said that they will allow you to prevaricate because, in fact, both are still used. The worm is the secondary logo, but it has not replaced the meatball.
So I really like the subtlety of the worm. I just think you can add it to things and it'll look nice and classic. And then the meatball is just...
It's a little busy.
Yeah.
Yeah.
But I still love it. It
has that classic.
It's classic NASA.
Yeah. So it's interesting. There's a little bit of a generational, perhaps, difference there because the worm came after the meatball. Mm-hmm. And so for you, that may have a more nostalgic feel.
It's all nostalgia to me.
It's all nostalgia. You're so young.
I am so young.
Oof, boy. But when the worm came out, it was adopted as the new NASA logo for a while. And then it was like, we want it back to the glory days of NASA and Apollo and the moon missions. We're going back to the Meatball, and that was like back to the great...
The heyday.
The heyday.
Yeah.
Perfect. And now it's the opposite. We've resurrected the worm.
And it's old school.
Because now the worm is old school.
Yeah.
That's right. Yeah.
Right.
Yeah. Anyway, well, today we'll talk about black holes and Ceres. But first, this episode of Walkabout the Galaxy is brought to you by the Higgs boson. When the winds of fate are threatening to blow you off your feet, anchor yourself with the Higgs boson. With no spin charge or color charge to make you dizzy and acting as its own antiparticle, the Higgs boson couples with your mass to give you some comforting inertia and help you stand up to all the forces in your life, pulling you in different directions. While the Higgs boson itself is highly unstable, a little Higgs field in your life will help keep you grounded in a topsy-turvy world. The Higgs boson. Be fit for life.
Fitbit?
That's a good guess. I'll give you a hint.
Reebok.
That's a worse guess.
Thanks.
Actually, it's not a worse guess. It's a comparable guess. I was looking for something related to like weightlifting.
Mm-hmm.
So when I was a kid, did you know I was on the high school weightlifting team?
I knew that.
I did not know that.
Quite a buff young man.
A long, long time ago, and we used Nautilus machines, which were quite the big thing in that day. And I was looking for a Nautilus. But did you know that Nautilus owns Bowflex?
Bowflex.
What's Bowflex?
Well, their tagline is "Be fit for life."
But that doesn't answer my question.
Is that not a hot thing anymore?
Bowflex is, but Nautilus isn't.
Well, I'm not sure that Bowflex even is.
Really?
Because she's younger and she doesn't know what it is.
Oh, Bowflex
Is it
Like
a
for a
young
while,
thing, or is
Bowflex
it a
was like
foreign
really
thing?
the thing.
Bowflex is still a thing. Absolutely, yeah. And it's just not into it.
I don't know.
Well, is it because I'm young or foreign or both?
It's a machine that you exercise on that has flexible rods to provide resistance instead of weights.
Oh. No.
Bows that you flex. Yeah. Well, our space news we were alluding to is the rollout. I guess we were more than alluding to it. The rollout of SLS, an initialism, as one of our astute listeners pointed out, a special type of abbreviation.
There you go.
The Space Launch System, which is NASA's new heavy lift launch vehicle, that's sort of like, okay, we had the shuttle, let's keep those solid rocket motors, let's take the engines off the shuttle, slap them on the bottom of the external tank, make it bigger, and put a little Apollo capsule on the top.
Yeah. It's just taking the Saturn V, taking the shuttle and gone
Smush
them together.
Yeah.
But it's still really exciting because especially, we've never seen, well, I've certainly never seen
a big old rocket
rolling out
of the VAB.
Yeah.
Yeah.
Unpopular opinion, I'm underwhelmed entirely by this.
By the whole system or by the rollout?
By the rollout. Like, the rocket's awesome, and I'm very much excited for when it goes off and all that kind of stuff, but, like, it's like rolling out to this thing, and it's just going to sit there for a month or two or whatever.
It's the first time we've seen it.
It's the reveal. It's the
reveal.
One whole...
That's right. It's like when Elon Musk shows off the Cybertruck. You can't go buy it. You can't drive it around, but there's this crazy cool electric stainless steel truck. So that's weird. Now we see this giant rocket we've never seen before. It's a new rocket. Come on, man.
It doesn't look different. Anyway, it's fine.
It does look different.
Look, a big old rocket.
It's fine.
It's fine.
The most underwhelming description.
I'm excited to fire it off and to lift things into space with it.
It's a nice new big tall rocket, and it rolled out of the VAB. It's comparable in stature to the Saturn V. And it's on the infamous crawler.
It's at 0.8 miles an hour.
0.8.
And it took about 11 hours or 14 hours or something to get there. And it arrived in the early hours this morning. Yeah. And then in a few weeks, they're going to do the, is it the wet test or whatever they call it?
Yes.
Where they fuel it.
Or something
yeah.
like that.
And they fuel it up and see if it can cope. And then they'll bring it back in and check that everything's still holding together.
They're going to bring it back?
Yeah.
Yeah, they're rolling it back to the VAB in about a month, right?
Yeah, just to check that it's managed to do what they hoped. No leaks, etc.
Okay.
Yeah.
Okay.
And then this summer, I don't know if we have a firm launch date.
No earlier than May.
Okay, so we're still at no earlier than May.
Yeah.
I think people are expecting it probably will be June.
Okay.
There are a couple of launch windows there.
They got to get in before hurricane season.
And also, I'm just thinking, I've got some conferences, and I just don't want. I don't want to be away. I need to be here. Yeah, I might just call in sick at a conference. Sorry, I've got a launch to go see.
So then it will be an uncrewed launch that will swing around the moon.
Mm-hmm. Artemis 1.
Right, and it'll be carrying at least one CubeSat that I know of, the Lunamap mission, which will be looking at the moon with a neutron spectrometer to look for hydrogen deposits in the south pole of the moon, helps understand better how much water is there. So that'll be fun. It'll be cool to see the whole thing, and then the Orion capsule coming back and splashing down. Then the Artemis 2, in principle, will be 6 months-ish later.
Artemis 2? Oh, I don't know.
The next mission.
I'm trying to think. What is the... Well, because Artemis 3 will be crewed. Or is Artemis 2 crewed as well?
I think Artemis 2 is.
I thought that would be way later than 6 months.
I may be wrong.
I don't know.
Definitely they're not landing on the moon it's a year. I think the timeline for people landing on the moon with this particular setup is not until now 2025 at the earliest.
So Artemis 2 launch date planned May 24.
2 years.
Yeah.
Wow.
I'm bummed out about that.
Yeah.
That's very disappointing. Yeah. Okay. Let's see. The other exciting news that you mentioned when we were starting off, Hannah, is...
James Webb.
Yeah.
Space Telescope, JWST, as we all call it. Have you seen the images?
Yeah.
Yes.
So exciting.
Yeah.
I mean, not like there's anything special in the image, but the fact that... Yeah, I mean, I guess a few weeks ago we got images where they kind of used each of the 16 pieces of the mirror individually to look at, a thing. And so you see 16 images of a star or something like that. And now they've arranged them all so that you can see. So it's acting as one big mirror. Right. And so now you get one awesome, ridiculously crisp, clear image of, I mean, they're pointing it at a pretty bright star, but of course there's all this background stuff. Right. I mean, no matter where you point your telescope in deep space, there's going to be...
So there's all these galaxies
and things in the background. Yeah.
What strikes you when you see the image is this spiky, bright star in the center, diffraction limited image, but if you look away from that, there's all these other little spots that are galaxies.
Yeah.
Almost exclusively.
Yeah, and it's really, I mean, it's awesome. It's working, right? I mean, all these, we worried for so many years, decades, whether this thing was going to work, because any one thing that goes wrong with this $10 billion thing screws everything up, but it is so far working perfectly.
Yeah, almost at the...
It's almost too good to be true, kind of better than expectations.
From what I've seen, those working on it are saying that it's operating, as you say, better than... at the max they could possibly have dreamed. So it's really exciting stuff.
Yeah, doing a hot mic switch.
Yeah.
Oh my.
Yeah. It's diffraction limited, and they have a person called the optical alignment and wavefront engineer, something like that.
Cool job title.
Yeah. Where they're actually tracking the phase of the light that's coming in from these mirrors to make sure that there's no destructive interference, is my understanding of it. My understanding, getting back to this being the self-deprecating podcast, is probably it's at least incomplete. Let's put it that way, since it's only gently self-deprecating. That's very exciting. I think they're on or ahead of schedule, and the telescope is performing at or exceeding spec.
Yes, so they have 6 months of commissioning, which would take them to June. And this is because they can image in a few different wavelengths. Is that right? And so
there are several instruments.
It's several, right. Yeah. So they will have to do this kind of refining for each of those. So we'll probably see other images in using different instruments.
Right. Yeah, right. Yeah, so they have the telescope itself, the mirror itself, kind of properly aligned, and everything is great. But now you have to try and attach all the different instruments to make sure all of those connections work and all the science instruments work. And I guess that takes a while. you want them to, like, as soon as it gets up there, turn it on, start doing some science. But of course, it
plug
takes,
and play.
Yeah, it takes months of engineering to make sure everything works properly, and then science can begin soon.
And in particular, with this telescope, it has a more finite lifetime than Hubble,
right?
Because it requires these cool temperatures, and it's station keeping at this L2 Lagrange point, and in order to do that station keeping, it has to use fuel.
Right.
And so at some point it'll run out of that. It won't be able to maintain that special orbit. Things will not stay cool, and
it can't be refueled. It's out.
Can't be serviced or refueled or anything like that.
It really does have a very finite lifetime.
Yeah.
And what is that lifetime roughly? Do we know?
Yes, we talked about it. It's like the design lifetime, I think, was 5 years, expected to be 10.
Okay.
And then, but probably, if things go well, actually more than that, because they used less fuel than they budgeted to get out there, which means they've got a little bit more fuel in the tank to maintain things. And then then it sort of, as you fly these things, you learn a little bit more about how to be just so with your...
Be nice and efficient.
Trajectory. Exactly.
Yeah.
So we've got sort of two main stories, a solar system story and a cosmological, an astrophysical story, not so cosmological. Let's start with Ceres.
Do you mean Ceres?
Oh, that's right.
How do you say it?
Hannah wasn't aware of this.
How do you say it? This is not about this is not about English accent or anything. This is just about proper English.
How crazy Jim is.
So
that's what this is about.
Yeah, say the planet, and then separately erase that from your mind, and then separately talk about a breakfast food item.
Cereal. Is that what you're saying?
Say it again.
I just want to hear what you're saying.
Ceres?
Yeah.
And cereal.
Okay.
What did you hear, Jim? What's your smug expression? How am I supposed to...
No, there's no smugness here. I'm wrong. I think we've determined that I'm wrong.
Yeah, I can't believe you brought it back up, but I guess maybe it's
a self-deprecating. I'm a moron. I don't know how to pronounce it. I think my problem is with the breakfast cereal. But
I don't know where you're coming from with all this, and I don't want to know.
Anyway, it doesn't matter. Go ahead. Tell me about the planet.
Dwarf planet? It is a dwarf planet.
I'm calling it full planet.
You're going full planet.
Yeah.
Okay.
Yeah, I think it's a full planet.
So Ceres, or cereal, as we like to call it, has always been of interest because it's in the asteroid belt, but it actually accounts for over a third of the entire mass of the belt.
It's the biggest one out there.
It's quite large considering. Radius of about 296 miles. And where Ceres has come from has kind of been a bit of a hot debate because it has some interesting features. So to a certain extent, it is like the other objects in the asteroid belt because it's there's some evidence to suggest that it's C-type, which means it's a carbonaceous chondrite, which is very common in the asteroid belt. But it also has much more water than would be expected and a lot more ammonia than would be expected in terms of stability of where they would be found.
Right. Those are both volatile compounds. Yeah. So where it's warmer, closer into the sun, you wouldn't expect those things to be incorporated into the solid objects that make up asteroids as much.
Yeah, they're usually a lot drier.
This is a mystery.
And Ceres is the one that we were speaking about, brines.
Yes.
Recently,
yes,
and
the
salty deposits on it.
And now there's this new paper out on Archive at the moment. So a team have been doing some modeling and looking at. They used like over 3,600 Ceres-size objects and placed them out in a location beyond Saturn's orbit, and then basically doing early solar system modeling and seeing how those different objects interact with the rest of the other planets. They found that with at least 3,600, at least one would end up theoretically in the asteroid belt.
Okay. Where did they end up? How did they come with this number 3,600? I mean, is that like how many Ceres do we have to put beyond the orbit of Saturn in order to end up with one in the asteroid belt?
Yeah, but they seem to be
really happy about that number.
Well, it seems to they seem to think that that's actually quite a reasonable number, especially early solar system.
I thought that we had estimated. I mean, like if you think about how many things are really out there I mean, not out Saturn, but outside of the Kepler Kuiper belt and stuff like that. That there are really like thousands and thousands of these big planetish sized things out there.
Right. So, so that sort of answers the question I was just going to ask, or to have you clarify, is what happened to the other 3,599, right?
Well, there's a lot. It's a pretty violent early solar system. Lots of collisions and scattering and various unstable orbits and things.
Right. Yeah. I mean, a lot of scattering. If you're beyond the orbit of Saturn, so interior to the orbit of Jupiter, where the asteroid belt currently is, that's a collisionally erosive environment at the moment. So the objects run into each other very infrequently, but when they do, it's destructive. And that's largely because Jupiter's gravity has put these objects on fairly eccentric or egg-shaped orbits so that they're not encountering each other in a sort of gentle, passing you on the fast lane here, on your left kind of mode, but smashing into each other from a completely other orbit. Beyond the orbit of Saturn, I think that those initial orbits would have been more calm. And then some models, and I don't know if this is the case in this particular one, but there are some models, the early evolution of the solar system, that have a fairly, as you said, violent shakeup due to very strong interactions between the big planets, especially between Jupiter and Saturn, that causes lots of resonances and gravitational perturbations to sort of sweep across the whole solar system, and that ends up scattering lots of objects to very, very different orbits, and most of those end up getting scattered out.
Yeah. So
there's a part of the Kuiper belt that's primordial. They're mostly circular orbits. These things are just formed out there where there wasn't enough stuff, and things were happening at a leisurely enough pace you didn't make big planets. But then there's a scattered disk as well that has more,
which makes sense,
eccentric,
where
orbits.
these rogue sort of dwarf planets have been kind of thrown out.
Yeah, and the Oort cloud is also like, when I think of what's called the Nice model, this big planetary reshuffling, I think of that as part of what's going on there is you're scattering things on a very, very eccentric orbit, so you can help populate the Oort cloud as well, although Jupiter does that pretty well by itself.
I mean, this is how you end up with things like Eris, right? So
exactly,
These big objects, I mean, like Pluto-sized objects that are in these ridiculously elliptical orbits, very, very far away from the sun most of the time.
Yeah,
and we think there are a lot more than just Eris out there, right?
Sure. Yeah, they've commented exactly on that Ceres has more in common with these Kuiper belt objects like Pluto, Eris, and Sharon or Karen?
I say Karen.
Karen.
Okay, then Karen. I don't know. The outer solar system is also still slightly out of my comfort zone.
I see, okay.
But yeah, I imagine as well, there's plenty more out there that we just haven't seen yet, which makes sense.
So, I mean, like Eris is this egg-shaped orbit, and it was seen on the part of the egg when it's closer to the sun, and therefore more detectable.
Right.
And they spend most of their time on the other parts of the orbit where they're much less observable.
Right. So my question is this. This is for the dynamicists in the room. I would have thought. I would have thought if you took something like Ceres and took it from.
Is this a cereal?
Took it from the outer solar system and put it into the asteroid belt, that it would have scattered away all the asteroids. So, and I understand that there are way fewer asteroids now than there were in the early solar system, but there's still a lot of primordial asteroids out there. Why didn't they get scattered away when? Well,
Ceres itself doesn't have the gravitational muscle to do that kind of clearing out.
No.
But it included in this paper is saying that their estimated capture probability and a final 80% depletion of the asteroid belt during the giant planet instability. So it's actually accounting for a huge loss of the asteroid belt would have been significantly larger.
During the process that puts Ceres there, during that process, you're losing 80% of what was in there. So it's a net erosion of the asteroid belt, but there's some transport of objects from the outer, the trans-Saturnian region into the asteroid belt but a greater transport of material from the asteroid belt out.
Yes.
Okay.
But Ceres itself, you know, we were saying it's the biggest asteroid. It's about 1,000 kilometers side to side, which is as big as Texas, but not a huge planetary type of object.
Mm-hmm. Okay.
Yeah. Cool. Let me drop your NASA historical trivia on you before we take a journey a little bit further out into the galaxy. So I have three. Your question is in three parts.
Three parts.
It's related and inspired by the worm Meatball question. The first one is quite simple. What year was NASA created?
It is simple.
It is simple.
But deceivingly difficult.
The second one is that when NASA was created, it was created from a previous an agency of sorts that existed. What was the name of that progenitor group from which NASA was created? And this one is multiple choice. Was it A, the National Advisory Committee for Aeronautics, B, the United States Upper Air Laboratory, C, the National Aeroscience Agency, D, the Presidential Special Committee on Rocket Propulsion, or E, the Executive Office for Air and Space Studies?
Did you come up with these?
I came up with all but one.
That must have been a fun afternoon.
And your final question is, what was the time period of use of the NASA worm logo before it has now been recently reinstated? So we alluded to this a little bit. The original NASA logo is the Meatball. At some point in time, the worm was created, and then it was retired. What were those dates?
I have no concept because they've always existed as far as I'm aware. So
since the beginning of time.
It was so I will tell you that the worm is back was 2020. That was when the worm returned. Okay. But prior to that it had been out of service. So what was the time period in NASA's history when the first life of the NASA worm? So you can ponder that while Jim tells us about ultralight dark matter.
Yeah, maybe. So this came about when we're thinking about supermassive black holes, which we often like to discuss on the podcast because they're friggin' awesome and they're huge. And they exist at the centers of most, if not all, large galaxies that we have seen. But hidden in a supermassive black hole is a mystery. Not actually inside the black hole. There's lots of mysteries inside the black hole, but
only mysteries.
Only mysteries. Yeah.
The only thing in there is mysteries.
But another mystery is how they came to be. So
the supermassive
ones, right? Normal black holes. I say normal, but stellar black holes that you would teach about or hear first about are, the collapsed remnants of the core of a very large star. So that's one way to make a black hole for sure. These supermassive black holes are very different beasts, right? They have masses of millions or billions of times the mass of a star, and they weren't produced as, in the collapse of the death of a star. They were early in the universe when the galaxies were first created. In fact, we've seen them, as far back as as far away as we can see galaxies, which means as far back in time as we can see. We see galaxies with these things in the centers.
Active galactic nuclei.
Right, with these and in fact, we've seen them so far away that they're starting to become a mystery. That is, we thought that you would just, the centers of galaxies are kind of like the deepest part of a gravitational well where everything likes to fall. And if you give things enough time, enough stuff falls in there that you can make a black hole. But we've seen them in such young galaxies that it's almost like you wouldn't have time to make them.
There wasn't enough time for that to happen.
And so it's a little bit of a mystery as to whether, you can engineer the conditions so that you could still make them kind of in the normal way but that's a little bit of a hand-waving thing. And so it'd be nicer if there was a better way of explaining how they form so quickly in galaxies. And so a new proposal here is that maybe there is a type of dark matter which they're calling ultralight dark matter,
It's like a shade of paint. Like
ultralight dark matter.
Yeah.
If you've ever looked for paints, this is an absolutely reasonable name for paints, given the ones that they have. Ultralight dark matter. Called ultralight because...
Do they have that in a set?
Ultralight is one word as well.
Ultralight is one word. Yeah. Right, and this is referring to like the mass of the particle that makes up dark matter. So we don't know what dark matter is, of course. That's one of the great mysteries of the universe.
Very important reminder here is that we don't know. Saying this is some weird version of something that we don't know what it is actually at all anyway.
Right. So why not have it make... Well, we're pretty sure it's some kind of little particle, some fundamental particle, right? Because we've talked about how we've ruled out, it's not like
You're giving
a whole bunch of...
a bad reputation here with this thing.
Oh, yeah. Well, we suck.
We don't know anything.
We're self-deprecating. Yeah. It's 95% of the universe. Dark matter, dark matter. We don't know what they are. Dark matter, we don't know what it is. Right? But it's not. We know it's not like normal stuff. It's not dead stars or brown dwarfs or, black holes, stuff like that. We know that it's probably these little fundamental particles, but we don't know which ones. And because we don't know which ones, we don't know how much mass they have. But... we have kind of ranges for these things. And
just to clarify, the dark matter, the dark in dark matter comes from, it's not interacting with light,
right?
In the ways that non-dark matter does. So it's particles that have a sort of different relationship with electromagnetic fields than the normal.
Meaning no relationship at all with electromagnetic fields, right?
They've ghosted.
They've totally ghosted.
Dark matter has ghosted photons.
Yeah, that's
not
right.
returning their calls.
That's right.
Not answering their text messages. You're dead to me, photons.
That's right. Yeah, I mean, dark matter in theory doesn't interact via the electromagnetic force or the strong nuclear force, so you can't make... nuclei out of these. Yeah.
Right.
They really only interact via gravity, which is how we detect them, and possibly the weak nuclear force, which is why some candidates for this are called these weakly interacting massive particles, or WIMPs. But WIMPs, when we're looking for what these things might be, we're often looking to like make them in particle accelerators and stuff like that. We're looking for things that are more massive than the particles we know and love. Like, what's a particle you know and love? Like, I love electrons.
I love the strange quark.
You love strange quarks? Of course you do. But those things have masses that are considerable. Like, an electron has a mass, and we measure masses in particle physics in weird ways in terms of energy, not in terms of mass, because E equals mc squared, and we love
that equation.
We love that equation so much. But an electron has a mass of, what is it, like half... of an MeV. So an MeV is 1,000,000 electron volts. So that's a unit of energy, an electron volt. It's how much energy an electron would get if you accelerated it across a 1 volt potential.
Hashtag boring physics tangent.
Boring physics tangent. Anyway, it's a unit of energy. And an electron has 500,000. So and then a strange quark has more than that. Strange quarks are much more massive than electrons are.
Yeah, they are.
Yeah, they are. And... the things we're looking for, like in our part for WIMPs and things like that, are much more massive than that. But maybe dark matter is mostly made up of particles that are way, way, way smaller than that.
Okay, so how many electron volts is an ultralight
dark matter thing would be on the order of 10 to the minus 20 electron volts.
Whoa.
So this is a hell of a lot of orders of magnitude smaller.
I'm not pretending to be astonished because I hadn't read this before.
Nice.
I actually am astonished.
Right.
Is that detectable with anything that we currently have?
It's not.
How do you test that theory? Yeah.
Right. You don't test it directly. It's not a thing that you're going to make in a particle accelerator and find, because it has so little energy that you're just not going to be able to detect it.
So it's a decimal point with 20 zeros. And a 1.
Right. Compared to the electron, which is already a light thing.
And the little tiny electron is
500,000 of them. Yeah. And this is 10 to the minus 20 of it. So
why is it that these why do you need ultralight dark matter particles to make supermassive black holes in the early universe?
Yeah, because the idea is that these particles would kind of decouple from normal matter very early in the universe. And so that basically they'll fall in and make themselves into blobs very early in the universe. And because they have mass...
being supported by radiation pressure?
That's right, right. So like normal stuff can't form into blobs in the really early universe because as it starts to collapse under gravity, pressure pushes it apart.
Right.
And so you can't make really big density blobs early in the universe with normal stuff, but with dark matter, possibly you can.
But why do they have to be ultralight for that to work? I would think any dark matter particle would be able to do that.
Right, but that's not really true because those dark matter particles still are kind of connected to the matter in some way. And so... In any event, it's getting a little bit too technical for poor Jim, but or the viewer or the listener. But yeah, I guess this very special kind of dark matter will decouple very, very early, give you the seeds for something very early. And once you've made the seed for that thing very early, then now I can make a black hole really early, and now I can have black holes at the centers of all my galaxies.
Because, as you said, there's much more of this stuff matter-wise in the universe than strange quarks and up quarks and top quarks and electrons.
Yeah.
And so there's a lot of mass, even though we just talked about how tiny each individual one of these particles is. There's a huge amount of mass in the universe in that stuff. And so if it globs in to very massive seeds, basically, for forming these supermassive black holes. So does... The galaxy is, part of the sort of lumpiness of the universe, right?
Yeah.
It's not the real big scale lumpiness that you get excited about, Jim. But for me, the galaxy is kind of a granular aspect of the universe. So does having dark matter clumpy that way tie back into any predictions or theories about inflation or how the universe got its tiny anisotropies in the distribution of mass in any way?
Not in any tremendous way. I mean, what it does is help us. So we have trouble with dark matter because dark matter.
Tell it to me.
Some of our theories about
every day. It worries me every day.
God.
It really does. It worries me because on large scales, some of our theories of dark matter explain like how clusters of galaxies evolve and so forth, and they work really well at doing that. But those same theories don't do well of explaining like the dark matter on very small scales, like why galaxies spin the way they do. Right? That's how we, and so different versions of dark matter don't work for all of the so it could be that dark matter is made up of more than one kind of particle. Could be.
Sure. Why just one? Why only one?
Why only one
particle?
So I think this kind of thing. I think that's the exciting part of this. This is just like a theoretical guess but I think this really hints at dark matter is probably made up of a couple different things, and you can explain supermassive black hole formation and the shapes of individual galaxies kind of with this one kind of ultralight dark matter, and then the large scale structure of the universe with some other kind of dark matter. I think that's the more likely explanation for what's happening in the universe than there's just one kind of dark matter.
And what I like about these sorts of publications and things, it's like you say, it's not necessarily providing an answer, but it's just making us like rethink about what are the boundaries that we're working within and kind of extending them a little bit, because it's so easy to just like we think in a certain way, and it's just like, well, actually there are way more other options out there that we're just not even looking at.
Yeah, sure. I love that about in cosmology especially, and this kind of I mean, it's like you get I've been focused on WIMPs and stuff, or I was for years, but like there are many ways. I like WIMPs.
Well, I mean, they're
true. My friends.
Why? Of course, we don't know anything about this stuff. Why would there only be? We're like, what is dark matter? And we're always thinking, is it this or this?
Right.
And of course, it could be 10 different kinds of particle. Right. So we don't know what we're talking about. There's more than one kind of fundamental normal matter particle.
Right. Right. So that's right.
Oh, cool. All right. Well, let's get back to the more mundane historical question.
But before you go on, I'll say one last thing about this. Okay. Because you asked a question that I never answered. That is, how would you possibly test this? So that's like, it's cool enough that this explains something we already know, but then that's like a post-diction. You need to make a prediction, right, for it to be good science. So one thing that would happen as a result of this collapse of this stuff really early in the universe is it will launch gravitational waves that may well be detected in the future. Not by LIGO or one of the gravitational wave observatories, because the frequency of these waves is not in that regime, but maybe by pulsar timing arrays, which
right.
is
the
another
Arecibo,
way, right? Exactly,
project.
those kinds of things. So this is a thing that is testable, maybe not right now, but at least in the near foreseeable future.
Very high frequency or very low frequency?
They're very low frequency.
So it's a very low rumble.
Right. These are like 10 to the minus 9 hertz kind of things.
Okay. That's very low.
Yeah.
That's
very
one
low.
oscillation every 30 years or something.
Right. So that's why you require, looking at
Is that because of
pulsars over decades?
Math or because
Oh
of the
no,
answer?
just like that's a very
Just the answer.
it's a very long time.
Right.
And
But
to make-
detectable if you're observing these astronomical phenomena over decades, you can see these things potentially.
Yet one
Imagine-
more reason we should live longer.
Yeah,
Yes.
imagine working on a project for 30 years and being there at the beginning and right at the retiring at the end
Yes, it's like
and getting your 2 data points.
I saw one wave.
Yeah.
One oscillation. Well, I don't know. It might be satisfying in some way. Well, speaking about time frames and that sort of span a lifetime, when was NASA created?
I feel like this is something, Hannah, that we should know.
I know. I've been asked this question so many times in trivia and I always get it wrong.
Oh,
Yeah.
And I
now's your
can't remember
chance
what my answer is. It changes.
1953.
57.
Hannah wins this one, 59.
Oh, the
All right. Well, at least we were in the right decade.
Okay,
I'm going to give us
Right,
both
yeah.
we're in the right decade.
She wins, but I'm going to give myself a...
It was post-World War II,
bronze medal.
pre-Kennedy.
Yeah.
Right.
Yeah.
Yeah.
Okay.
NASA was created from an existing agency. What was the name of that progenitor agency? Was it the National Advisory Committee for Aeronautics, the United States Upper Air Laboratory, the National Aeroscience Agency, the Presidential Special Committee on Rocket Propulsion, or the Executive Office for Air and Space Studies?
Yeah, again, congrats. Those all
Yeah.
sound like they are potentially legit things.
Yeah.
I go with that first one.
I'm going with the presidential one.
The Presidential Special Committee on Rocket Propulsion. It is the first one, actually. The National Advisory Committee for Aeronautics.
It was NACA.
Okay.
NACA.
And then
yes,
went for NASA.
It became
Okay.
The National What is it? What does it stand for?
That should have been
National
the first
Aeronautics
question.
and Space Administration. But I actually got that wrong because in my thesis, I remember
It's been
writing
a
it.
long week. It's been a long week, folks.
Because I was writing astronautical instead of astronautics.
Oh,
And my supervisor kind of had to correct me. It's like, you should probably know what NASA stands for.
yeah.
Yeah.
Well, and plus I was like making up all of these NASA sounding words. So I had to like, wait a minute, is it aeronautical, astronautical? What is it? What was the time period of use of the NASA worm logo?
41 years.
I want a start date and an end date.
79 to 20.
It was reinstated in 19.
Oh, sorry.
2020.
Oh, sorry. Oh, okay. That's...
So at sometime before 2020, it was retired for all except sort of special use kind of things. And it was resurrected in 2020. The worm is back, NASA Administrator Jim Bridenstine, with the launch of the SpaceX Crew Dragon, I believe.
75 to 89.
I was going to go I'm going to go 77 to 90.
You're both very, very good. Very on point.
Thank you.
Nicely
Yes, we
done.
are.
I'm going to call it a tie. 75 to 92.
Oh,
Okay.
Yeah.
Not bad.
Yeah. So it came in post-Apollo, pre-shuttle, right?
finished in 92.
It came in before Apollo, after Apollo and before the
75,
shuttle,
yeah.
75.
Yeah.
And
One
then
of the
it was
greatest years that ever
retired
happened.
Mid-shuttle,
You said that was 92.
92.
Okay.
Yeah.
That's when I was born.
Early shuttle, really.
So
Are you serious? You were born in 92?
Yeah.
I was born in 75. So it was
Oh, what?
the entire time between our
Wow.
births.
Cool. That has to mean something.
That has to mean
There's
something.
no
That
way
has to-
that's a coincidence. Yeah. Well, while it may have felt like a real-time history of NASA, it was just another episode of Walkabout the Galaxy. Give us 5 stars and we'll give you the universe. Be sure to follow us on Facebook and Instagram to get all our updates. And check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel, Walkabout the Galaxy. Our videos now feature chapter markers, so you can skip to the good stuff, whatever that may mean to you. Catch up on old episodes wherever you get your podcasts. Follow us on Twitter
at walk_the_galaxy.
And ask us questions anywhere using hashtag AskWTG. Our theme music was composed by Richard Jerusik. Production assistance is provided by Logan Basinger. Thanks to our listeners in Arizona and around the world. Stay safe. I'm Josh Caldwell.
I'm Hannah Sargent.
And I'm Jim Cooney.
We're the AstroQuarks signing off until the next episode of Walkabout the Galaxy.
I really almost said I'm Maddie Duff. Accidentally.